Welcome to section 5.6, rational zeros. So this is a very useful tool for us to be able to come up with zeros of a function. Again, we've been working through chapter 5 with polynomials. We've taken a look at just graphing based off of the t-chart or using synthetic substitution. Then we looked at how we can factor and find zeros of a function and use those zeros. We haven't done anything with the graphing part of it yet. This rational root theorem, or rational zero theorem, is a way for us to take a polynomial that might not be factorable by grouping or any of the methods that we've looked at, and come up with the possible zeros that I could use and test with synthetic division. So a very important concept for us to understand in terms of helping us with the polynomial graphing. So the rational zero theorem states that if you have some polynomial in the descending degree order, it has integer coefficients, then every rational zero of that function has the following form, where we're taking the factors of the constant term. So our constant term of a subscript o, we'll find all the factors for that. Those will become our p-values. We'll take our leading coefficient, a subscript n, we'll find its factors. They become all of these q values, and then this ratio of p over q's become the possible factors that we would then use in synthetic division to find out some zeros. So very useful for us. The thing that just gets a little confusing is what is p and what is q. Just if we remember that p is related to constant factors, q is related to our leading coefficient factors, and that's what we're going to do to set this stuff up. All right, here we go. List all the possible zeros. So all we're doing right now is listing what they could be. These are the ones that may give us a zero. They don't have to all of them work, but let's see what we get. So we look here, and our leading coefficient, which is where I'm going to look at my q's, is 1. I look here, my constant coefficient is a p. First, I make sure my polynomial is all in descending degree order, and we're good there. All right, so then if all of my p values, let's look at those. They're all plus or minus things. So 1 times negative 6, or negative 1 times positive 6. Positive 2 times negative 3, or negative 2 times positive 3. So we can have these as my possible factors of negative 6. Q, well, just 1 and 1. Negative 1 times negative 1, or positive 1 times positive 1. So we have to include all this plus minus value in here. All right, then, what do? I look at the ratio of these p to q's. And here they are. These are the possible factors. So when your q has just one factor of 1, then you can use p factors, and they become your p over q ratios that you can test. So plus or minus 1, plus or minus 2, 3, and 6. These would be all of my possible, now I'm only writing the plus or minus out there in the front of the first one, but please understand that it's plus or minus 1, 2, 3, and 6, all of them. And those are all of the possible zeros that I would then use to test in my synthetic division process. We'll get there in just a second. All right, so identifying on the second example here, now I have something other than a 1 in front of my leading coefficient. So once again, where are my p's? They're the factors of my constant term. Where are my q's? They are the factors of my lead term. So we set them up. Plus or minus 1 and 2 and 4 and 8. And then plus or minus 1, plus or minus 2. So now, with my p over q, I'm going to go each p value divided by each q value. So 1 over 1, 1 over 2. And then we would do that with each of the other p's. So 2 over 1, 2. 2 over 2, which is just 1, so I don't need to repeat it. And then we have 4 over 1, 4. 4 over 2, well, I've already got that in there. 8 over 1, 8 over 2, I already have the 4. So those are all of my possible P over Q's that I can test in synthetic division once again to come up with possible zeros for this polynomial here. So take each P, divide by each Q. All right, finding the real zeros now. Well, now we're going to actually get to use our synthetic division process to find our real zeros. Here we were testing what the possible ones are. Now we will actually go and find them. Now sometimes you're going to notice that some of these are set up as a 4-term problem, which means it could be factorable by grouping. And if that's the case, then by all means do the factor by grouping. And I think that's what's going to be able to happen here in this group. If I look at this and I group the very first 2 together, I can factor out an x squared and be left with an x minus a 5. I can group those 2, pull out a 7, and be left with an x minus a 5. And then I recognize my factor by grouping, x squared plus 7, x minus 5. And if I was looking for the zeros, that would mean f of x would become 0, and x minus 5. And if I set zero product property up, I discover that x squared equals a negative 7, and when I took the square root there, I get x equals plus or minus square root of I times the square root of 7. So that's not real. But over here, I would get x is equal to 5, and that is real. So those are my only real solutions. This x equal plus or minus I root 7 is an imaginary solution. So I could do factor by grouping in that one. Now let's try one where we don't do factor by grouping. This one I can't factor by grouping anyway. So let's see if we can do our P's and Q's. So P's, Q's. All right, we have plus or minus 1 and 2 and 5 and 10. Q plus or minus 1 again. So our P over Q's become just the P value. So plus or minus 1, 2, 5, and 10. Now what we do with these is we set these up as our synthetic division problem. So synthetic division again, what do we do with that? Well, first we make sure we're in descending order with our polynomial. We are. Then we use the coefficients and the constants to set up our synthetic division problem. So we have a 1 for the x cubed, a negative 4 for the x squared, a negative 7 for the x, and a 10. There were no missing powers, so I didn't have to worry about including a 0. Now I'm going to do the shortcut method here of my synthetic division. I'm not going to do the middle step. All right, these are what we are testing, and every time I come up with a remainder of 0, then we know we have found a root, or a 0 of our function. And therefore we can be able to answer this problem using synthetic division. That was the original problem. Find the real zeros. All right, let's just start testing. Let's try a 1. So drop 1 times 1, 1 minus 4, negative 3. 3 times 1, negative 3 minus 7, negative 10. Negative 10 plus 10, 0. We have found one of our zeros. Very good. All right, at this point you have one of my zeros found. I could then, here's the beauty of synthetic division, we have found that this, which is now x squared minus 3x minus 10, maybe that's factorable. And it is, actually. So if I'm looking for zeros here, I can do x minus 5 and x plus 2 equals 0. And that means through zero product property, I get x minus 5 equal to 0, x plus 2 equal to 0, x equal 5, is another possible answer. X equal negative 2 is another possible answer. And if you look over here, those numbers were part of my possible zeros group. So I could have done synthetic division again, testing each of these numbers in this group, but it's just faster once you find one of the zeros that you set up a new polynomial. Hopefully you're going to get yourself down to a quadratic, and then that quadratic will be able to be factored. Or maybe if I couldn't factor it, I could do quadratic formula, come up with things. So the zeros here are 1, 5, and negative 2. And those are my x-intercepts for this graph. I will then use them in the future to help me draw the graph of this polynomial. All right, so rational zero theorem. Great tool for us to have. Let's go try some more. Find the zeros of this. Now that's definitely not a grouping problem. We've got 5 terms here. Wow, got some Q and P values that definitely give me more possibilities as P over Q. So we're going to have some work to do here. Let's see, plus or minus 1, 2, 3, 4, 6, and 12 are the factors of 12. Q plus or minus 1, 3, 9. So possible zeros. Again, each P with each Q. So we have plus or minus 1, 3, 9. I'm just kind of, I do it in this order where I just take each P and I just go da-da. And then I'm going to do the same thing with the 2, and then the 3, and then the 4, and the 6. So my numbers aren't necessarily going to be in any kind of order here. 2 over 1, 2 over 3, 3 over 3, which is 1, so I don't need to repeat it. 4 over 1, 4 over 3, 4 over 9. Yes, you're going to have some possible zeros that are fractions. 6 over 1, 6 over 3, which is 2, already accounted for. 6 over 9, if we reduce it, becomes 2/3, which is already accounted for. 12 over 1, 12 over 3, which is 4, already accounted for. 12 over 9 reduced becomes 4/3, also accounted for. So there it is. There's my long list of possible zeros that I will now set up synthetic division with and test. Now this one is this polynomial is starting out as a 4th degree polynomial, which means when I do the synthetic division process, I'm going to do synthetic division, find a zero hopefully, then I'll be at a cubic. I will reset my synthetic division based off of that new cubic polynomial and do this process again until I get down to a quadratic, which I will hopefully be able to factor or quadratic formula, something like that. All right, let's check it out. So we get 9, setting up synthetic division, 3, negative 30, 6, and 12. Here we go. Let's go ahead and start with our 1. 9 and 3 is 12. And 12 minus 30 is negative 18. And negative 18 plus 6 is negative 12. And negative 12 plus 12 is 0. Now, it just so happens that we find 0 on the first time through. With our last example, we did this as well. That's not guaranteed to always be the case. Okay, we found a 0. So then what I do is I recognize that I have here, this is a 9x cubed plus a 12x squared minus an 18x minus a 12 polynomial. And now we're going to set up new p's and q's for this polynomial. Now it just so happens that the p's and the q's are the same thing we had over here. Again, that's not always going to be the case, but it happened here. So we set up our new synthetic division problem. 9, 12, negative 18, negative 12. And we're going to go again. We're using just, again, it happens to be the same values in this problem. So what if we tested a 1 again? Well, it might work again, because it might be what we call a double zero. So let's just test the one more time. 9 and 12 is 21, and 21 minus 18 is 3. 3 minus 12 is a negative 9. Okay, so 1 is not a double zero. Let's go test negative 1. Negative 9 plus 12 is 3. And negative 3 minus 18 is negative 21. And 21 minus 12 is 9. No? All right. Let's now decide. Here's our very large group of options that we're going to test. Well, let's just decide which way we want to go with this thing. We could just go in order, right? Let's go test a 2, and then a 3, and then a 9. I know you guys are probably going to want to avoid those fractions, but it might be that one of those fractions is one of our solutions. So let's go test a 2 here and extend this down. So 18 and 12 is 30, and 60 minus 18 is a 42, and 84 minus a 12, well, that's definitely going to not get me there. What's that, 84 minus 12? 72. What about a negative 2? We have negative 18 plus a 12, which is a negative 6, and then a 12 minus an 18, which is a negative 6, and a negative 6 times negative 2 is a positive 12, and a positive 12 times plus a negative 12 is a 0. All right, so we found another 0. And now we have a quadratic, 9x squared minus 6x minus 6, that we can set equal to 0. But looking there, I can see that I could pull out some GCF. Here, I'm going to come over here. Let's pull out a 3. And I get a 3x squared minus 2x minus 2 equals 0. Can we factor the 3x squared? I don't know. Let's see what happens. 3x and x. Let's see, we want a negative 6 plus a 1 gives me a negative 4. No. So that's not going to work. So I can't factor this thing, which means I'm going to have to go ahead with my quadratic formula. Now at this point, I'm going to divide everything by a 3, and I can get 3x squared minus 2x minus 2 equals 0, and we'll go ahead and set quadratic formula up here. That would equal negative b plus or minus the square root of b squared, so negative 2 squared, minus 4 times 3 times negative 2, so actually plus 24, all over 2 times a, which is 2 times 3, or 6. So 2 plus or minus the square root of 28, all over 6. 28, I can reduce it. Simplified radical form. Square root of 4, square root of 7. Square root of 4 is a 2. Square root of 7 stays aside. Then I got that 6 there. Then, we can factor out a 2 out of the top. 1 plus or minus the square root of 7. And that 2 at the top cancels with the 6 on the bottom, making it a 3. Finally, giving me 1 plus or minus the square root of 7 all over 3. So those are 2 of my zeros, in addition to the ones we found when we were doing the synthetic division process, which were negative 2 and 1. All right, so we set this thing up. We got our zeros of negative 2, 1, and then 1 plus or minus the square root of 7 over 3. And there we go. So rational root theorem, rational zeros theorem. Again, very helpful tool for us to have. And then here's our last one. We're going to go real quick on this one. P's, 1 and 3, Q's, 1, 2, 4, 8, and then P over Q's, plus or minus 1, 1 half, 3, 3 halves, 3 fourths, 3 eighths. So those are my testing points. I'm going to go in 8, nothing is missing, 2 minus 21 is 37. That one's not going anywhere. Negative 3. Negative 24 and 2 is negative 22. 66 minus 21 is 45. That one's not going anywhere. So sometimes the process takes a while. 8. 3 halves of 8 is 12. 12 and 2 is 14. 3 halves of 14 is 21. 21 minus 21 is 0. And then 0 minus 7 is negative 7. Negative 21 halves. Nope. Negative 3 halves. That's negative 12. Negative 12 plus 2 is negative 10. That becomes 15. 30 over 2 is 15. 15 minus 21 is negative 6. This becomes 9. 9 minus 2 is 7. And then I get stuck again. So I kind of ran out of time, folks. I'm sorry. But if we kept going on this thing, we're down to testing these values here. Hopefully, eventually, we're going to find one that is a 0. And then I would then be able to use my synthetic division for the cubic and keep going. So I either made a mistake going through that pretty quick, or I just have yet to find my zeros with the remaining 2. So I'll let you guys try those. I apologize, but I got to stop us here. So hope that helps. See you later.